So my talk will be a bit more theoretical, but I think it fits well in the context of what Janos told us before with all the experimental work that has been done on salt. So I'm gonna discuss different mechanisms of how permeability may develop in rock salt and yeah, what the effect of water is in natural salt systems. And for this, I will look at a simple fluid flow model for rock salt to calculate permeabilities and come up with a microphysical model that yeah, analyzes the deformation of individual fluid inclusions or pores under the influence of diffusive mass transfer for a certain reason that will come up later. And then I'll give a short overview of my yeah, PhD project and future work that is planned. So that's a plot where you see the dihedral angles that Janos mentioned briefly as well. So for natural rock salts, yeah, well, we see that these wetting angles depend on pressure and temperature. And if we look at natural conditions, upper crustal conditions, we would assume that these angles are in a way set up that pores are disconnected, and this is why we can basically say or assume that rock salt would theoretically be impermeable. This is also in accordance with what Janos said before. However, if we increase temperature and pressure conditions, with the water that is already in between the grain boundaries could redistribute in a way that yeah, a connected fluid network could be established. So another way, of course, if we have subsurface activities in rock salt, we change the local state of stress, and thus we damage rock salt. This can lead to increasing permeabilities in a brittle way. So to quickly talk about possible permeability development in rock salt in general, I want to discuss these three mechanisms. So we have this case when we damage rock salt, and it behaves in a rather brittle manner because of the differential stress changes, and then it's just basically microcracking or dilating. Then we have the other concept that I just have shown before, with depending on the dynamic wetting angles, that could lead to increasing permeabilities, and a very controversial recent third mechanism that states if you have increasing differential stresses, the fluid inclusions would literally change their shapes and stretch so much until they connect with each other and with the grain boundaries, so that you have also an percolation network that is developing and leading to increasing permeabilities. So I want to quickly go through these mechanisms because they are important to study, as some of them might yeah, threaten the integrity of rock salt, for example in salt caverns at the top where microcracking is present, and that's why it is important to study these fundamental processes that yeah, that are there. So a lot of literature is available that studies the mechanical behavior of salt, as Janos already pointed out. A lot of creep tests and experiments have been done, and it's generally well known that there's a certain dilatancy boundary depending on the stress conditions. So when we have low differential stresses, we can say that rock salt is more or less impermeable and deforming by ductile flow. But if we increase the differential stress, then it would microcrack and behave a little bit more brittle, and that this can increase permeabilities. So, yeah, as I just said, pore fluid pressure changes could be responsible for that, or differential stress changes. But still, it's not clear if we can just relate from these experiments to natural conditions, because as Janos also pointed out, natural rock salt is typically considered to be wet, so we have to take effects of water into account and how this influences the dilation, the microcrack behavior, the mass transfer between these salt grains. And this is why we want to look in general how healing sealing influences the permeability, and we do this now also by looking at these three mechanisms of permeability development again. So it's pretty clear, and it has been well established, that once rock salt enters the brittle regime due to strong differential stress changes, that the permeability increases quite significantly. So that's basically out of question. But then we have this other concept relating to the dynamic wetting angles, where it's also said once it connects completely, you have increasing permeabilities depending on recrystallization, or you have a disconnected pore network under smaller pressure temperature conditions. And the third mechanism that I mentioned before briefly, that basically assumes you deform the salt, and with this the inclusions are deformed as well, and this can also lead to interconnected pore network, which is a bit hard to imagine, but that's the point why we looked at it in a bit more detail. But for now, I want to focus on this to give some simple calculations of possible permeabilities under natural conditions. So we have a fluid flow model where we basically assume the grains are completely wetted and it's a completely connected pore network, compared to a situation where the dihenal wetting angles are organized in that way that it's more like individual tubes maybe that are connected, but we assume that it's basically well connected so that we get maximum permeabilities, and we're just calculating flow or permeabilities based on Poisson flow theory, so that we are able to describe flow depending on the geometrical properties, so in this way grain size or the thickness of micro fluid films or channels, and so in between salt grains. So if we look at the results, we see the permeabilities on the left, and depending on different tube radii or fluid film thicknesses, we see for a range of 1 to 100 nanometer thickness, that's what Janos said as well when we investigate these fluid film thicknesses between the grains, that we are in a range that is more or less below nanodarcy permeabilities. So we would in these regards conclude there are no significant permeabilities developing under natural conditions by this mechanism, under ductile flow. Looking at this mechanism, we want to incorporate the impact of diffusive mass transfer. So I'm going to present the model as it has been published in a science paper a few years ago. And one way to look at this is to use the capillary number concept. So basically a dimensionless ratio that compares the stress-driven stretching rate, literally the form of an inclusion, if it would be stretching, or if surface tension forces are strong enough to counteract stretching and keeping it in the original shape. Which means that if this number is above 1, an inclusion would be stretching with the material, because the internal forces of keeping it in its original shape is not strong enough. And if it's below 1, that would mean the inclusion basically stays in its spherical shape no matter what differential stress you apply. So in the end, it's important to see which of these rates is faster. However, we think this concept is not sufficient enough to look at how fluid inclusions behave or deform in natural rock salt. Here we have some inclusions that are on a grain boundary, an array of inclusions that I took in our lab, and there are also in the literature a lot of examples where you see round fluid inclusions on grain boundaries, or within a grain isolated. And we think that or it's basically known that these inclusions are brine filled, so you kind of have to incorporate the diffusive mass transfer processes that are not included in the capillary number concept. So we had the idea to extend this concept by including these solution precipitation transfer processes. So we are looking at, I'm going to quickly go through this model so it's clear what we are doing. So we are looking at a regular round unstressed inclusion that as soon as some differential stress is applied changes its shape. I want to note that the shape change should be very minimal. It's just a bit more yeah, extremely shown here. And this change of shape changes the chemical potential at the side and the top of the inclusion, so that yeah, material is basically transported from one side to another, in this case NaCl, salt material, and precipitates again, so that in the end it's a pretty quick process that just keeps the inclusion round. So it's not meant to illustrate a change of size, it's just meant to see the inclusion is just not stretching because material is flowing constantly inside the inclusion from one side to another. So we put this concept also in a term that is similar to the capillary number concept, and we call it now the mass transfer number, which again means if the number is above 1, you have stretching. If it's below 1, you have a inclusion that is not changing its shape or stays spherical. So if we look at the results, we took parameters for room temperature brine-filled inclusions, and we see both numbers, or yeah, like on the left side for a range of differential stresses. And when we look at natural, more or less realistic natural conditions, we do indeed see that the numbers regarding the capillary number concept are above 1, maybe up to 1000, which goes in line with the assumption that this paper made, that okay, it's above 1, so the inclusion is stretching with the material and connecting and forming a fluid network. But if you look at the mass transfer numbers, we see that they are many orders of magnitudes below 1, so that we would conclude that there is no stretching of an inclusion. It's also possible to combine these into one number, but then we are still in many orders of magnitudes below 1. So yes, that brings me to the conclusions. Of course, when we have subsurface activities, drilling, formation of caverns, we damage rock salt. This can lead to increased permeabilities in the damage zone around walls. But looking at undisturbed conditions, we figured out that the water content that is there and the geometry of the pore structure is too small to support significant Darcy flow. And regarding the deformation of these inclusions, we can say, as rock salt is typically wet and the inclusions are brine filled, we can assume that mass transfer is active, which is also the reasons that we mostly see around fluid inclusions, because they're just staying in their shape. So the capillary number concept is not applicable here in this case. So this means that there's no real percolation network developing. The integrity of rock salt in this regime of ductile flow is not threatened, at least not through the linking of individual pores. But I want to point out again that once we have activity and we enter the brittle regime, which can happen once we work in the subsurface, that there might be permeability and damage. So it's not to be mixed up with the models that I've shown. And now I want to give you a quick overview of my project. So this talk was basically to assess transport properties of rock salt during creep. I also assessed how healing with brine permeation at cavern walls are competing with each other to have another idea of it. But the real idea is to do more experiments now that also address these topics. So regarding mechanical healing of rock salt, we have already done some experiment at Kiel University, and I'm planning to complement this data soon with my secondment at the UCL, and with some more extensive experiments in our own lab that include permeability measurements with gas or brine to really have an idea of chemical versus mechanical healing in rock salt. Yeah, that's it. Thank you for your attention.